Unit 3 is going to give us more in-depth analysis of differentiation, applications of it, what it tells us about a function, points of inflections, how to sort of associate the relationship with the graph of the first derivative to the function to the second derivative, how those things can help us sketch a function. We're going to talk a little bit about optimization. We're going to use that to approximate tangent lines. And then at the very end of this unit, we're going to tie that into the beginning of the opposite of differentiation, which is called integration. So we're going to talk very, very briefly about that, and then in much more depth in the chapters to follow. So this very first section today, 3.1, is about the second derivative test and about concavity. So the first thing we need to talk about is, what is concavity? How do we use derivatives to tell us anything about it? So concavity is the shape of a graph, talking about whether it's opening upward or opening downward. A graph that opens upward, or it is cup-shaped, is said to be concave up, opening up. Something to notice if you think about a tangent line for a part of a graph that is concave up can only exist underneath the function or below the function. And this is true because if it was above the function, it wouldn't be tangent. It would hit the function more than one time. If I tried to draw a line tangent on this side, it would definitely hit the function more than once, and it would then not be a tangent line. The slopes of tangent lines are increasing as we get closer and closer to that vertex, or we're going to give it a specific name later, but as they get closer and closer to that point that functions like a vertex. And what I mean by that is this is very negative. As I get closer down here, it's going to become less negative, which means it's getting bigger, less negative, less negative. As I curve around now, it's getting positive, more positive, more positive, stronger positive slope, or greater positive slope. So that's what it means by they are increasing. And because they are increasing, that means that our second derivative is actually going to be greater than or equal to 0 in that concavity. So the most important takeaway here is that if we have a second derivative that is positive, the graph of our original function is concave up. Now let's look at the flip side of that. A graph that opens downward or is frown-shaped, sad face, is said to be concave down. Since we are now opening downward, our tangent lines are going to have to be above the graph for the same reason that the tangent lines had to be below the graph before. The slopes of these tangent lines are decreasing, so we're starting with something strong and positive. As we draw more and more tangent lines going around the function, we're going from less positive to negative slopes, which means that those tangent lines are decreasing, but most importantly, it means that our second derivative is less than or equal to 0. So when we have a function that is concave down in a certain portion, the second derivative is negative. So we can say that if the second derivative is negative, we are looking at a portion of a function where it is concave down. So this is a non-mathematical memory tip, but happy faces are positive. Positive makes a smiley face, concave up. Sad faces are negative. They make a frowny face. Obviously, there's not a whole lot of math there, but I thought it was kind of a fun visual to help you remember concave up and concave down. But again, the biggest takeaway from second derivatives from this whole portion we're talking about is that the second derivative tells us the concavity of the original function based on the sign of the second derivative. Now, unlike these two functions that we just looked at, many functions are not the same concavity over their entire domain. For example, the cubic function has a point where it does in fact change concavity. It's concave down and it's concave up. So it has different concavity along different intervals of the function. And there is a point at which that concavity is changing, and that point has a special name, and that is called a point of inflection, or an inflection point. Sometimes you will see people use IP to abbreviate inflection point. A couple of things have to be true for something to be an inflection point. The first thing is that the graph has a tangent line at that point, meaning, in simple terms, the derivative has to exist. The first derivative of the function has to exist at that point. The other requirement is that the concavity at that point has to be 0, undefined, and have a sign change. Sorry, it has to be 0 or undefined. The second derivative is 0 or undefined, and there is a sign change. So all three of those things have to be true. The derivative has to exist. The second derivative is either 0 or undefined. That's what's making it change concavity. And it has to be changing from positive to negative. It's possible that your second derivative is 0, but then the graph isn't changing concavity at that particular value. So it has to change sign from positive to negative or negative to positive. So thinking about this example that I just drew, I'm going to go up top to do some work here. F of x equals x to the third. Let's think about whether or not that point 0, 0 is an inflection point. So let's first look at the derivative. Well, the derivative is going to be 3x squared. It exists, so that meets our first requirement. The second derivative is going to be 6x. This is defined everywhere. It's 0 when x equals 0. And then we need to check, is there a sign change in the second derivative at x equals 0? Well, if I plug in a -1 to our second derivative, we would get a negative number, -6. If I plug in +1, I would get a positive number. So there is, in fact, a sign change from negative to positive. So we could say that 0, 0 is an inflection point for the graph f of x equals x to the third. So I'm going to recap how we just showed that. We took the first derivative, it has to exist. We take the second derivative, find where it's 0 or undefined, and make a sign chart to see if it does in fact change sign at that value. That all of those things have to be true in order for it to be an inflection point. So let's look at this graph of a function. So this is not the graph of the derivative or the second derivative. We're just going to say this is the graph of our original function. Take a minute, pause the video, see if you can identify from the graph where it's concave up, where it's concave down, where it doesn't have concavity, and the point of inflections. So go ahead, pause the video and do that. All right, I tried to use some color to make this a better visual for you. Concave up from -2 to -1, from 1 to 3, and from 4 to 5. Concave down in green from -1 to 1 and from 5 to 6. There's 2 intervals, and you may not have even noticed that the graph kept going after 6. That's okay. There's 2 intervals where the concavity there is no concavity. And if you think about that, from 3 to 4, it looks like a portion of a line. From 6 to 7, it looks like a portion of a line. A derivative of something linear is a constant, which means the second derivative would be 0. So we're not going to have concavity happening at those values. When the slope is constant, there is no concavity. Points of inflection. There are 2 points of inflection. One of them is at 1, 1. The other one is at 5, 1. There are 2 other points where it seems like there could potentially be points of inflection at -1, 1 and at 4, 2, but both of those are sharp turns, which means it's not differentiable there, which means even though clearly something is happening in the function, it is not a point of inflection. Think back to those requirements of what it has to be. The very first one is that it has to have a first derivative, which it will not at those 2 points. So now we're going to just work through how to find sort of the whole process that we talked about already, but analytically, how do we find the intervals of concavity using the second derivative test, which we're going to formalize more. But this is similar to what we did when we were just using the first derivative test to find relative maxes and mins, except we're going to take it one step further and really focus on the behavior of the second derivative. So what we want to know is what is the sign of the second derivative and where is it changing sign. So the very first thing we're going to do is we're going to take the derivative. Then we're going to take the second derivative, set it equal to 0, find those critical values. Those are what we call possible inflection points, PIPs. We're going to make a number line, and that number line is going to tell us about the concavity. So the first derivative is 4x to the third on number 1 plus 3x squared minus 6x. The second derivative, 12x squared plus 6x minus 6. We're going to set that equal to 0. That's going to give us that x equals 1/2 and -1. The second derivative is defined everywhere, so there's no other values that could be inflection points besides 1/2 and -1. So those are our PIPs, our possible inflection points. We're going to set up our number line or our sign chart. We're going to test a number less than -1 in our second derivative, like -2. That would give us a positive value. We're going to plug in a number in between -1 and 1/2, like 0. That would give us a negative number. We're going to plug in a number bigger than 1/2, like 1. That would give us a positive value. So based on this sign chart, we can now immediately identify the concavity. So it is concave up from -infinity to -1 and from 1/2 to infinity. It's concave down. So we know that because the second derivative is positive. So I'm going to say since f double prime greater than 0. It's concave down from -1 to 1/2 since f double prime is less than 0. Now the inflection points are where our possible points of inflection change sign. So it is changing sign. It was positive and now it's negative at -1. It was negative, then it's positive at 1/2. So the possible inflection points are -1. If I plug -1 into the original function, I get -2. And 1/2. If I plug 1/2 into the original function, I get 7/16. Since f double prime changes sign. F double prime changes sign. So at those values, well, not at those values. At those values, it's 0. But before and after before and after that value, it's changing from positive to negative or from negative to positive. So the key thing there is that it's changing sign. Positive second derivative, concave up. Negative second derivative, concave down. A sign change, point of inflection. So those are really the big takeaways here. Number 2 is giving us a function and a second derivative, and it says to list the intervals where the graph is concave up, concave down, and possible points of inflection. So something I want you to notice before we even get started, as I mentioned in Unit 2, looking at this original function, we need to identify there is a domain restriction here. In the original function, x is not allowed to be, there is a domain restriction of plus or minus 2. X cannot be plus or minus 2. So we have to remember that when we're analyzing our second derivative. So we're going to look at our second derivative, f double prime of x. If we're looking for possible points of inflection, we want to know when that's 0. So we want to know when 10 times 3x squared plus 4 over x squared minus 4 to the third power is 0. That would be true when the numerator is 0. And looking at this, 3x squared plus 7 is never going to be 0 in the real number system, which is pretty much all we ever talk about in calculus. So since this is never 0, and the only place that it's undefined is at plus or minus 2, which is not defined in the function anyways, there are no possible inflection points for our function. That doesn't mean that there aren't concavity changes, though. So we are going to look at the second derivative. We're going to look at a number line, and you should be thinking, well, what numbers are we going to put on this number line, Judson? And those two numbers are going to be the places that the function is undefined, because it could have behavior changing around where it is undefined. So there are vertical asymptotes at -2 and +2, but we can still test what's happening to the left of -2, in between -2 and +2, and above +2 when in the second derivative. So in the second derivative, if I plug in something like -3, I'm going to get a positive value. If I plug in 0, I'm going to get a negative value. If I plug in something like +3, I'm going to get a positive value. And this allows us to talk about concavity. So this function is going to be concave up from -infinity to -2, and from 2 to infinity, it's going to be concave down from -2 to +2. Remember, you typically need to justify this, so we can say it's concave up since f double prime is positive, and it's concave down since f double prime is negative. Okay, let's talk about the second derivative test for relative extrema. And a couple of students asked about this in Unit 2 when we were talking about the first derivative test, but now we're going to formalize it. A couple of things to note. This test does not require that you use a number line. It also does not find points of inflection. Even though we're going to talk about the second derivative, we're still only talking about relative maxes and mins, which is what the first derivative test helps us identify. So it's still only helping us identify relative maxes and mins. So you're going to find the critical numbers for the derivative. Then you're going to plug those into the second derivative to determine the concavity. So think about that. If our second derivative is positive, meaning it's concave up, that would mean this value that we're talking about is a relative min, because it would be right down here. Similarly, if our second derivative is negative, which would make it concave down, we would have a relative max. So the purpose of this test is saying we can find our critical numbers, but instead of making a sign chart, we can just plug those numbers into the second derivative and figure out if they're positive or if they're negative. That will tell us the concavity, which will tell us if we have a relative max or a relative min. So let's look at this and practice. Use the second derivative test to find the relative min and max points for f of x equals negative 3x to the fourth plus 6x squared. So you're first going to find the derivative and the critical numbers, then find the second derivative. So go ahead and pause the video and do that. So we're going to get from our first derivative that our critical numbers are at 0 and positive and negative 1. We're going to take our second derivative to get negative 36x squared plus 12. Now we are going to plug those critical numbers into our second derivative to determine the sign, therefore the concavity, which will tell us if we have relative maxes or mins. So when we plug negative 1 in and positive 1 and we get negative 24, that means that this is concave down, which means we have a relative max when x is plus or minus 1. And if we plug 1 or negative 1 into our original f of x, we get 3. We have a relative min, since at 0, the function is concave up. We have a relative min when x is 0. And when x is 0, the function is also 0. So we have a relative min at the point 0, 0. And we know this by the second derivative test. So find your first derivative and your critical values, plug those into your second derivative to determine the concavity, and that will tell you if you have relative maxes and mins. So part of you is probably thinking, why didn't you tell me this last unit? This test doesn't always work. Sometimes you don't get enough information. We're actually going to see a case sort of like that right now. But that's why we didn't go over this in the last unit or in the last chapter, because it doesn't always work. So number 2, or I guess it's not numbered, the second example here gives us a whole bunch of information. And for me, I sometimes get overwhelmed when all of this information is just written out. So the very first thing I would do on a problem like this is put it in a table. It's just going to make it easier for me to understand what's going on. We are given x values. We are given derivatives at particular x values, and we are given second derivatives at particular x values. The question that is being asked of us is to find the x values of the relative max and mins when possible. So we are using this to determine, can we find relative maxes and mins? So the second derivative test is going to come into play here. A couple of things must be true. The first derivative has to be 0. So that gives us our candidates. Right now we can tell our critical numbers are negative 1, negative 3, 0, and 2. Now based on whether the second derivative is positive or negative, that will tell us if we have a relative max or min. So let's first look at where we have positive concavity happening. So the second derivative is positive at negative 3, and when x is negative 3 and when x is 2. We have positive 4 and positive 3. So thinking about that, positive concavity means they open up, which means we're talking about relative mins. So we have relative mins when x equals negative 3 and 2. Since f double prime is greater than 0. And f prime equals 0. We know that when x is negative 1, we are concave down, since g double prime, or the second derivative of g, is negative 2. So we know we have a relative max, since we're saying concave down, relative max when x equals negative 1, since f prime is 0 and f double prime is less than 0. Now there's a couple things that we don't know. It's really important to point out we don't actually know what's happening when x is equal to 0, and this is why the second derivative test is not always the best. It is possible that there is an extrema at x equals 0. We have no idea. We don't know because the second derivative being 0 doesn't tell us anything about the concavity. So that's something important to notice. We also don't know what's happening when x is equal to 1. We know it's concave up, but we don't know what's happening with the first derivative, so we can't come to any conclusions there. So big takeaways from this section, and you will notice if you go into the notes, there are some extra practice problems that you are more than welcome to work through. There are answers in the Drive or in Google Classroom with these notes. But the key takeaways from this lesson: first of all, identifying concavity, knowing that the second derivative tells us about concavity. Concave up means the second derivative is positive. Concave down means the second derivative is negative. Being able to use that to also talk about inflection points, analyzing the behavior using a sign chart for the second derivative. And lastly, using the second derivative test to identify if we have a relative max or min from the first derivative. So make sure that you are freshened up on those skills, do extra practice as needed, and I look forward to seeing you in class. Thanks.